Before proceeding any further, we will step briefly aside to examine one simple piece of mathematics, one that is often not explicitly justified. We're going to look at how we change mathematically from something that is a large sum of terms, each of which is very similar to its neighbour, to an integral. This is something that is essentially true in the limit as we go to very large numbers of terms that are varying smoothly. This changeover necessarily involves something we can think of as a density of states. This change is something that might just be intuitively obvious to you, but then again it might not, and there are some subtleties, so we'll go through it explicitly here. This change can be convenient because integrals are often easier to evaluate than sums. We can do this transition when the different states involved are closely spaced in some parameter, such as momentum or energy, and when all the terms in the sum vary smoothly with that parameter. This is relatively obvious from basic integral calculus, but we explicitly discuss this here for clarity and completeness, and because we're about to use it.
Suppose we have some states indexed by some integer q. For each of these states, some quantity, such as perhaps energy, has a value fq. Hence, summing all of these quantities would give some result, a sum s, as a sum over all of these possible values of the integer q for each of these quantities fq. It could be that fq can also equivalently be written as a function of some parameter u, such as momentum, for example. And this parameter u takes on some specific value uq for each q. So then we could equivalently write fq is the same thing as f of uq. For example, again, fq might be the energy associated with the momentum uq, and q might be indexing all of the allowed values of k, corresponding in this case to a momentum h bar k that would essentially be this quantity uq, and the energy would be h bar squared k squared over 2m, for example. So we could write our summation as a summation still over q, but of f of uq. So q indexing, for example, all of the k states, uq being the momentum associated with each k state, and f being the energy associated with a given momentum. Suppose now that the uq and the fq are very closely spaced as we change the integer q. This could occur in a solid, for example, with k values that are very closely spaced because the crystal is big. And we also presume that both of these quantities, the uq and the fq, vary relatively smoothly with this integer q. We suppose that this smooth change of uq with q, such as momentum with this index indexing the allowable values of k, is such that we can approximately represent u as some smooth and differentiable function of a continuous variable q. That is saying that u of q is the same as uq for all integer values of q. This is now a function of a continuous parameter here, q, but for every particular integer value of q, this is the same as uq. We can define the difference between two specific adjacent values, uq plus 1 minus uq, as being small delta u. Now, the difference in q values between adjacent q values actually is rather trivial, but for the moment we can write that as q plus 1 minus q. Well, obviously this is equal to 1, but we'll think about it this way for the moment. So this is the difference between two adjacent allowed q values. Well, trivially, the separation between adjacent u values, delta u, is delta u divided by delta q multiplied by delta q. This is a trivial mathematical relation. Because of the presumed smoothness of this function u of a continuous variable q, then u of q plus 1 minus u of q, or small delta u, is our expression just as written here. But approximately speaking, we can write this ratio of this small change in delta u for this change in q as the derivative du by dq, with q now considered as a continuous variable. If the changes here are small in u as we go from one adjacent q value to the other, and this function is smooth, then we can replace this precise ratio here with the derivative. But of course, delta q is just equal to 1. That's rather trivial from this expression here. And so u of q plus 1 minus u of q is simply du by dq, where now we're considering u as a function of a continuous variable q. So, considering some small range of possible values of u, and we'll call that capital delta u, within which the separation small delta u between adjacent values of u, the allowed values corresponding to the integer q's, was approximately constant. That is, within some small range here that is possibly considerably larger than small delta u. However, the separation between adjacent values of u is actually approximately constant. Then the number of different terms in the sum that would lie within this range delta u is capital delta u, that's the range we're considering, divided by the separation between adjacent possible allowed u values. But, of course, we've already deduced that delta u can be written as du by dq. So this expression here can be replaced with this one. So this is the number of terms in the sum that lie within the range capital delta u. Equivalently, we could define something we call a density of states that would simply be 1 over du by dq. And then we could say equivalently that the number of terms in the sum that lie within this range capital delta u, which we had written as capital delta u over small delta u, and we had also rewritten in this form, well, with this definition here, we can rewrite it also in the present form. It's g of u times capital delta u. Hence, instead of summing over the integer q, we could instead consider a set of values of u, each separated by capital delta u, and spanning the same total range of values of u corresponding to a range of integer q's. And we could write the sum over all these values, s, as, of course, by definition being the sum over q of f of q, and being exactly equivalent to the sum over q of f of u of q, as approximately the sum over this set of u values, the ones separated by capital delta u, and we have our same f of u here, the number of terms in the original sum that corresponding to a range delta u is g of u delta u. So these two expressions are approximately identical. And then formally in this expression we had just derived, we let capital delta u become as small as we like. And then we can approximate the sum by an integral to obtain this integral expression. This is essentially the definition of an integral as the limit of a sum. So in going from a sum to an integral, we have to insert the density of states in the integration variable into the integrand. So the sum here over q of whatever we were trying to sum up becomes the integral of this same quantity we were trying to sum up multiplied by the density of states and times du, the infinitesimal in the integral. So as long as our functions involved here, these terms in here or in here, obey the kinds of smoothness constraints that we have discussed, then we can replace a sum with an integral, at least approximately in the limit. And of course, the integration limits we have in here have to correspond with the limits we would get for uq in running over all of the possible values of q here.